Okay, good afternoon. So there were some questions at the end of it yesterday, which I wanted to go over for everybody, but we'll do it at the end of the lecture. Let's not break the flow. We'll do it towards the end. Were you able to do that gradient descent with matrix? Okay. All right. So we'll pick where we had stopped yesterday. So we had told that in the support vector machine, the optimization problem to find the optimal margin is given like this. Half of W transpose W subject to Y W transpose Xi plus B greater than or equal to 1. For question how to solve it. Right? So how do we solve this? And okay, so about the feedback also I'll talk at the end. Thank you for that. So we want to solve this optimization problem. To solve this optimization problem, we'll apply the KKT conditions, the necessary conditions. So what was the first KKT condition? Sorry? So who are all CS? Is there anybody from CS undergraduate? Raise your hand, no? Okay, all right. So anyways, there was a feedback saying that we don't remember optimization, so don't assume that we know it. There was some feedback. So that's okay. If you didn't remember, you should have attended the class, no? I mean, I didn't make you sit in this 2 Monday lectures first so that you don't feel bored and say it's a repeated or repetition of what you've done. I can't come to your hostel and teach you again, no? I've taught you once, I'm repeating it in the class, so you come to the class and remind yourself about those things, right? So it's you have to take, I mean, I can't spoon feed that much. I'd already spoon feed, I feel. Huh? So I can't go beyond that. So you have to focus. So tell me, what were the conditions? Now at least everybody's on the same page. What were the 5 KKT conditions? First was the equality constraint. Is there an equality constraint? No. So A is nothing. What was the second inequality constraint? So you would have Yi W transpose Xi plus B greater than or equal to 1. I going from 1 to the number of data points which you have. What was the C condition? Yeah, we'll come to the C condition, which is more involved. Let's write the D and E condition. What was the D condition? The D condition was the product between the Lagrange multiplier and the constraint is equal to 0. Correct? So what were the Lagrange multipliers we had used for equality constraint lambda i's, for the inequality constraints mu i's? Correct? So now we'll just change, I think in this notation we have not, in this machine learning we are referring to them as alpha. So if alpha are the Lagrange multiplier corresponding to the inequality constraints, so you would have Yi W transpose Xi plus B minus 1 equal to 0, I going from 1 through n. Yes? The number of data points is the same as number of constraints. So that's why you've got I playing a role everywhere. There's no J. What was the E condition? Non-negativity on the alpha. So alpha I greater than or equal to 0 for all I going from 1 through n. Okay? What was the C condition which we need to work out? So let's work out the C condition. What did the C condition say? Somebody from this side is CS undergraduates. What was the C condition? चलो याद नहीं थर्ड सेमेस्टर का कोई बात नहीं, मंडे के लेक्चर्स अटेंड नहीं करे कोई बात नहीं, रिकॉर्डिंग तो पढ़ के आ जाते. So what is the C condition? Like I said, necessary and sufficient conditions were the hero in the whole optimization course, and we repeated it many times. The gradient of the function was equal to the linear combination of gradient of the constraints both the equality constraints and the inequality constraints. Yes or no? Or if you want to write it in form of the Lagrangian function, the gradient of the Lagrangian was equal to 0. Yes? So let's try to write it. What is the gradient of the function here? So gradient of the function is gradient of half of W transpose W. Correct? So what will that be? So the gradient is with respect to the W's, the W1 to whatever the dimension W has, Wm, right? So that will be, what will this be? It will just be W, yes. We did that just on Monday, right? We did this, or the previous Monday we did this. Everybody okay? You write it, it will be W1 square plus W2 square till Wm square. You differentiate with respect to W1, you'll get 2W1, 2 will cancel out, only W1. With respect to W2, 2W2, 2 will cancel out. So you'll just get the W vector. Is that okay? So now what we want to do, we want to take the right hand side and do the gradient of that as well. So this I am doing with respect to W, for example. What all variables do we have into play? We have got W and what all variables do we have here? And correct, we also have B, correct? But we were taking gradients with respect to the variables which are there in the original function, not with respect to alpha, right? So that is what we are saying. The gradient of the function, so how I would write is, let me erase this first, let's write the whole thing first, then you will understand. So we will write gradient of the function W transpose W is equal to the linear combination alpha I going from 1 through n, gradient of the constraint. Is it still foreign to you? We just did this on Monday. Yes or no? Okay. So we'll write yi W transpose xi plus b minus 1. I am taking this 1 to the other side from this constraints equation. I am taking this 1 to the other side and writing greater than equal to and then picking the constraint. That's the standard form of the optimization problem, where you write the inequality constraints to be greater than equal to. Everybody with me? Okay. So now the gradient has to be with respect to what? The gradient has to be with respect to the W and the B, because those are the two variables which are playing the role, not with respect to alpha here. Correct? Because it's with respect to W and B which are playing the role in your original optimization problem. Alpha is the Lagrange multipliers which we have added later on. Can everybody see this? So if I do, so this means that if I write this with respect to W and B, if I have to write W and B here, for example, rather than writing with respect to this, I can write this as W comma B. So when I do the left hand side here, this will give me what? This will give me W, because you will do with respect to, अच्छा तुम लोग भूल जाते हो, let me write it then. So what we are doing, we're doing gradient with respect to W comma B of half of W1 square all the way till Wm square. Now we have switched to m. Correct? So once you would do with respect to W, you will get half of 2W1 all the way till 2Wm. Yes or no? With respect to B, you would get 0. So this is nothing but W comma 0. Everybody with me? Okay, now let's do the right hand side. I have to scroll. This is the right hand side. So we'll do the same thing. So our right hand side is summation of I going from 1 to n alpha I gradient of w comma b of yi times w transpose xi plus b minus 1. Now when you will do with respect to w, what will you get? Yi xi, correct? This will be w1 xi1, w2 xi2, wm xim. When you differentiate with respect to w1 through wm, you are left with xi1 to xim, the mth dimension. Can everybody see? Should I write it down? Here, in the middle. Are you here? Are you getting it? Okay. Okay, let's write it down. I think I'll not do in a hurry because there is an example which you would do. So what we'll do is we will write this down as yi w1 xi1 plus all the way till wm xim. Now the superscript is denoting the dimension, the subscript is denoting the point. The points are given by I, the superscript, the dimension is going up to m, I is going up to n. And this minus 1, this will be same. Now when you do this, you will get summation I going from 1 to n, alpha I will differentiate, so I will get yi, and then I would get xi1 through xim. This will be with respect to w. When I differentiate with respect to b, what will happen? So this is plus b minus 1. So this will be with respect to wi's, I'll just get the corresponding xi1 to xim. Should be neater. With respect to b, when I'll do, what will I get? I'll just get 1. Y is anyways in front. Correct? It's a scalar. B is just a scalar. Correct? And then with respect to 1, nothing will happen. So this will be equal to summation of I going from 1 through n, alpha I, yi, xi and 1. Correct? Now I'm going to equate the two, left hand side and the right hand side. Correct? So what was our left hand side? It was w0. So we'll say w0 is equal to summation I going from 1 through n, alpha I, yi, xi1. So what will you get? You get that w is equal to summation I going from 1 to n, alpha I, yi, xi. Here alpha and y both are scalars and x is a vector, and you will also get that 0 is equal to summation alpha I, yi. Everybody with me? So now we have applied those 5 necessary conditions to this optimization problem, and we got how many conditions? We got A was nothing there, we got the B condition. Instead of C, we got these 2 conditions, correct? And instead of D, we got this complementarity condition and the non-negativity conditions. How did we solve this? We did it on Monday. How did we solve it? Didn't we plug it into a software and it gave me an answer? Yes? Yes or no? I will not go forward. You tell me, how did we solve this? We did cases, remember cases? We said which constraints are active. Arey yaar, padh ke to aao. What more do I do? Tell me. If you're not being with me in the class, then I can't repeat the whole thing many times, right? Unless you tell me that you're not understanding. So anyways, so whatever I just talked is written here. So here, instead of writing the gradient of the function is linear combination of gradient of constraint, which I wrote here, this line. Can you see? Instead of this, I wrote this as a Lagrangian function, which we also discussed on Monday, that you can write the Lagrangian function as the objective function minus the constraints, and then you can apply the gradient of the Lagrangian is equal to 0. So B is the same, what we wrote, D is the same, E is the same. Instead of just equating these two here, I am writing that the gradient of the Lagrangian is equal to 0. I explained this Monday. So you can do it this way as well. If this is easier for you, you follow the scribble in my recording. If this is easier, then follow the notes. You get the same answer. You get W, get the same thing. W is equal to this. Everybody with me? Okay. Now, what are these? These are necessary conditions. What did we do in the case of regression? When we were trying to find a minima, what did we do? We applied the sufficiency conditions. The sufficiency condition was Hessian is positive definite, है ना? And gradient is equal to 0, Hessian is positive definite when we were doing the unconstrained problem. Then on this Monday we talked, this was the following previous Monday. This Monday, day before yesterday, we talked about for the constrained problem, the sufficiency condition is that you have to satisfy the 5 necessary and sufficient conditions, and Hessian of the Lagrangian with respect to x is positive definite over the null space of Jacobian of constraints, which I just said it and I didn't spend too much time on it. The reason for this is here the Hessian matrix of the Lagrangian will turn out to be positive definite. So it will be positive definite over all of the space, so the sufficiency condition would be automatically satisfied. So you don't have to remember that complicated F condition which I wrote. In case you've forgotten, I'll just show you once so that you're with me. कहाँ चला गया मैं? Offline supporting material. So those who were there on Monday, we had written these 5 necessary and sufficient conditions. So this was the second order sufficiency. We were saying you have to satisfy the 5 necessary and the Hessian of the Lagrangian is positive definite over the null space, blah, 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 which I didn't spend too much time. So this condition is not needed here. Here this will turn out to be positive definite anyways. So this is what I have written. It is a convex quadratic program with a positive definite matrix. If you look at the gradient of the objective function here, the gradient of the objective function turned out to be just w comma 0. When you ignore with respect to the b, just with respect to w, it will be just the identity matrix. Anyways, I'm not going into this. You don't have to worry. So it will be the sufficiency, these are sufficiency condition as well. It is a convex problem. So whatever 5 necessary conditions which you will apply will not just be a candidate for minimizer. They will be a minimizer. They will be a global minimizer. Is that okay? Without going further into sufficiency conditions, because that's not the focus of the class. Okay, so now what we'll do, we'll solve a problem. Okay. So the problem is given like this. Let's not call them support vectors. These are just vectors. So they're given 3 points here because these, you had done cases with me with one problem on Monday, but now we are doing it in the support vector machine context. So you're given that you've got 3 points. We're not calling them support vectors for the moment. And you're known that these two belong to one class and this belongs to another class. So this is like training your machine, training your model. It's giving you these 2 points, a benign data set of no cancer. This is a malignant one, it has a cancer. So you're given that x11, the y value is 1, at x2, y value is +1, both are belonging to the same class. For 2, 0, it's -1. So you can think of this as benign, this being malignant, this being normal, this being abnormal. Now the question is, find the ideal hyperplane using the necessary and the sufficient conditions. Is that okay? So how many cases will we have? So we are solving the example. So your original problem is minimize half of W transpose W subject to yi times W transpose xi plus b minus 1 or greater than equal to 1 for I going from how many i's? 3, right? So how many constraints we have? 3. How many cases will we have? Sorry? 2 cases? Any other option? How do we figure out a case? I think I'll have to start bringing candies or some chocolates to encourage you to ask questions. I got questions written in the feedback. I'm sorry I forgot to ask. I was shy to ask. Arey bhai pucho. That's what I'm saying. I want to reward you for asking questions. Ask me. Don't ask me at the end. Ask me in the middle of the class. I mean, this may sound counterintuitive to what others might say, but for me, if you're not asking, and like I said, I'm not teaching well, you're not getting it. Basically, which I'm defeating the purpose of teaching. And my goal is for you to get it. If you don't ask, it means you're not getting it. So there is no stupid question or dumb question. I'm sure if one person asks, there will be 10 others who will have a similar doubt. So I'll repeat those questions which guys asked at the end of the class today. I'll tell you that these are very genuine questions. So anyways, how many cases will we have? 8. Now somebody woke up. Why 8? 2 to the power 3, there are 3 constraints. Each constraint will be active or inactive, 2 into 2 into 2, your basic permutation combination from your 12th. Assuming everybody did math in 12th here. So we'll do the cases, right? So we'll do the cases here. So we'll do one case which I'll show you. So we'll do case 1. Case 1, we're doing all constraints are inactive. So when the constraints are inactive, what does it mean? What does it mean? Sorry? Yeah, which means that they are strictly greater than 0, and then we go back to our D condition, which is this guy, and which means that all alphas will be equal to 0. Correct? So from D we know that alpha 1 is equal to alpha 2 is equal to alpha 3 is equal to 0. This also satisfies the E condition because they are non-negative. So now we'll go back to the C condition to find the W. What was W? W, the margin is summation of this which we found. So all alphas are 0, so this is equal to 0. W is equal to, should I write it as a 0 or as a vector as a 0? What, how many dimensions? N dimensions. N dimensions or M dimensions? M. What is the dimension of the problem? Two, right? It's a XY plane. So M is 2, or the D in the regression case is 2. So it's 0, 0. So that is done. So what are we left with? We have to check whether we are satisfying the constraints or not at every point. So what are the constraints? So the constraints are given by this. So the first point, yi is how much? It's plus 1. W is 0, so this term is 0. We got B minus 1 greater than equal to 0. This implies B is greater than equal to 1. When we go to the second point, what is y value? It's 1 again. W transpose xi is again 0. You get B and you get minus 1. So you get the same thing. Correct? What is the third point? Minus 1. The class value is minus 1. This is again 0 because W is 0. So the xi's are not playing any role here. B minus 1 greater than equal to 0, which implies b is less than equal to minus 1. So what do we get? Sorry? It's a contradiction, right? The b is, which is supposed to be the distance your hyperplane is from the origin. Somebody asked me that also after the class. I'll tell that also again in detail. You cannot have two b's, right? There is one hyperplane you have to find. At one point you're saying b is greater than equal to 1. Other way you're saying b is less than equal to minus 1. So this is a contradiction. So no solution for this case. Everybody with me? Okay. So now let's do a case which works. Okay. So this is what is all worked out here, you know, which I just said. You get alpha is 0, you get w 0, all alpha 0, and then you get a contradiction. Everybody fine? So let's do it a case which works. So the case is that all are active. Okay, so when all constraints are active, so from the D condition we would get that y1 w transpose x1 plus b minus 1 greater than equal, or active, sorry, equal to 0, y2 w transpose x2 plus b minus 1 equal to 0, y3 w transpose x3 plus b minus 1 equal to 0. Alpha 1 could be anything, alpha 2 could be anything, alpha 3 could be anything. Correct? So what I'll do, I'll substitute y1 x1 y1, y2 x2 and y3 x3. This is given to me. So I'll get three equations in w and b. So once you do that, you get these three equations which are written on the left. So you will get, I've put a bar here just to signify that it's a minimizer. It doesn't mean anything. Usually like we put star in the optimization case, no, it is a minimizer, it's a candidate for minimizer. Rather than just writing the variable, I'll put a star on it. So here I'm putting a bar on it. But we don't have to do it, so don't worry. So you'll say w1 plus w2 plus b minus 1 equal to 0, 2w1 plus 2w2 plus b minus 1 equal to 0, minus w1 minus b minus 1 equal to 0. So this is what we get from the, after substituting y1, y2 as 1, y3 as minus 1, after substituting x1 to be, which is given to be, x1 is 1 comma 1, so you get, that is why you get w1 plus w2 plus b minus 1 equal to 0. x2 was 2 comma 2, so you get twice w1 plus twice w2 plus b minus 1. This is plus 1, this is minus 1, and this is 2 comma 0. So you just get twice of w1, get twice of w1, w2 will not play a role, and with a minus, minus b minus 1 equal to 0. Everybody with me? Okay. So we've got three equations, three are known, but we have to look at the other equations as well. So we started with D. We can't do anything with E, which is saying non-negativity on alpha. So we'll go back to the C condition. The C condition is this. Correct? So we'll first write W. You can write first one like this, alpha 1. So what will be this condition? The C condition says summation alpha I yi is equal to 0. This would mean that alpha 1 plus alpha 2 minus alpha 3 is equal to 0. Correct? Another condition said that W is equal to summation of alpha I yi xi. I going from 1 through 3. There are 3 points. So you will write it down. This is W1, W2 is equal to, so you'll write what is alpha 1, we don't know, y1 is 1. So you'll write as alpha 1, what is x1 plus alpha 2, 2, 2, plus alpha 3, 2, 0. So you'll get W1 is equal to alpha 1 plus 2 alpha 2. Minus, sorry, because y is minus. Minus 2 alpha 3. W2 is equal to alpha 1 plus 2 alpha 2. That's it. So how many equations we have? We have 1, 2, 3, 4, 5, and 6. So we have 6 equations, and these are all linear equations. There is no product of the variables, so it's not nonlinear or quadratic or any of that sort. 6 linear equations, 6 unknowns. I'll apply Gaussian elimination or whatever I'll do and solve them. Or you can take one out and try to substitute it, back substitution you can do, but the easiest is to make a matrix and a vector and then a right hand side and solve for it. Everybody okay? So this is what I do in the notes. So I'm saving time here. Okay. So this was the first 3 equations which I wrote. Then I wrote this equation. And then I wrote these 2 equations. So now I've got this W1, W2, B, alpha 1, alpha 2, alpha 3. And I put the matrix together. There is a right hand side. And I solve for this. And I get this value. So when I solve for this, I get minus 1, 1, 1, 1, 0, 1. So this is W1, W2, B, alpha 1, alpha 2, alpha 3. Correct? Trying to be sloppy and then it gets all messed up. W1, W2, B. So now what do we have to do? So you realize that all your 3 alphas are greater than equal to 0. So your E condition is satisfied. Now what do you have to do? Check for the B condition. The B condition is the constraints equation, right? So you have to check whether the constraints are not satisfied or not. So the constraints for yi w transpose xi plus b minus 1 greater than equal to 0, you have to check for all i's, okay? So now let's try to substitute it. So the first one, y is plus 1, w is minus 1 comma 1, and x1 is 1 comma 1. So this will be minus 1 plus 1, b is plus 1, minus 1. So this value is, these cancel out, this is equal to 0, so it is satisfied. Correct? Which should be true because this is an active constraint. So remember, we are assuming all active constraints, so it has to turn out to be 0. If it is not, then there is a problem. Okay. The second point was 1, w is minus 1, 1, but x2 is 2 comma 2. So minus 2 plus 1 minus 1. This is again equal to 0. This is fine, this is fine. The last one is minus 1, w is minus 1, 0, but x is 2 comma 0. So you put, this will be minus 2 plus 1 minus 1. So what is this? Minus 1 plus 1, this is again equal to 0. So all constraints are satisfied. So this, what you got here, is not just a candidate for minimizer, it is a minimizer. Everybody okay? So now what you'll do is, before I start talking about other things, so this is what is written all here, we worked it out. You do this one case by yourself and tell me what you're getting. Then I'll not make you do this again. So this is the last time you're doing it. Monday we did it one problem to tell you how it works. So we're saying first constraint is active. No, inactive, sorry. We're making in this example. The first constraint is inactive, which implies that y1 w transpose x1 plus b minus 1 is strictly greater than 0 and alpha 1 is equal to 0. No, the second one we are making, sorry. The second. So the first and the third constraint are active. So active. So in this case, you would get y1 w transpose x1 plus b minus 1 is equal to 0. Alpha 1 could be anything, and similarly y3 w transpose x3 plus b minus 1 is equal to 0. So alpha 3 could be anything. Can you solve it and tell me? Think with me. So there's a joke here. I'll talk about the feedback. One feedback was, like I said, you're too scripted. Improve your jokes. At least be polite in giving a feedback. I'm doing it for you. So it's like an instruction. But never mind, I बच्चों की बातों का बुरा नहीं मानते, so I didn't take it personally. But there is this joke here. मास्टर जी खुशी का ठिकाना ना रहा, कोई को इस मुहावरे का अर्थ बताओ. तो चिंटू खुशी घर वालों से छिपकर हर रोज अपने दोस्त से मिलने जाती थी. You guessed it. फिर एक दिन उसके पापा ने देख लिया और उसे खुशी को घर से निकाल दिया. अब बेचारी खुशी का ठिकाना ना रहा. ये जवाब सुनकर मास्टर जी बेहोश हो गए. All right. So did anybody do it? So let's substitute it now. So this is 1, x1 is 1, so this will be w1 plus w2 plus b minus 1 equal to 0. y3 is minus 1, so this is minus 1. It will be twice w1 plus b minus 1 equal to 0. Those are the first two equations you will get, correct, after substitution. Then you will go back to the C condition. The C condition was, so this is the D condition which we are applying, hai na? So this is the D condition. So the C condition was, the first condition was the summation of alpha I y is 0, right? So 1 alpha 2 is anyway 0, so it will be alpha 1 minus alpha 3 equal to 0, correct? And then it was W is equal to summation of alpha I wi xi, I going from 1 to 3. So again, W1, W2 is, so alpha 1 will remain alpha 1, sorry, this is yi. Yi is 1, this is 1 comma 1 minus alpha 3, 2 comma 0. So how many equations you have? 5 equations, 5 unknown. Did anybody solve it? Yeah. What do you get? Okay, let me write it down. I think this is all solved here. So you get W1, W2, alpha 1, sorry, B bhi to chahiye. So you got B, alpha 1, alpha 2, alpha 3, and you get this as minus 1, 1, 1, 1, 0, 1. Everybody comfortable? Now the E condition was that all should be positive. So the E condition is satisfied, and now you have to check the B condition. When you do the B condition and check for the constraints, it will turn out that all are turning out to be 0, while you assumed the second condition to be inactive. So that's why it's not giving you candidate for, it's conflicting with your assumption. Everybody okay? Fine? Okay. So this is what we'll stop here. So what we'll do on, so now we'll switch to Tuesdays and Wednesdays for the class. Monday, there's no extra lecture this Monday, so we'll not meet Monday. We'll meet tomorrow, sorry. We'll meet tomorrow for the lab. You'll do 4 problems on regression. And then we'll talk about the survey paper. Okay? So so we'll talk about this, and then on Tuesday we'll start with something called as the dual problem. So in reality what happens is, you don't solve the SVM this way. You transform it into another problem, which is called the dual of it, for example. And then you solve it, and then you will go to the non-linearly separable, which is soft margin and kernel trick. So this will finish SVM. Now coming to few things. Yesterday I ran over time, today I'll finish early. So here the first one will be correct, the second will not be satisfied, and the third one will be correct. So this will not give you a minimizer. So now what I wanted to do is talk about the questions which people had yesterday. Then I'll talk about the feedback also a little bit, then finish you before 3:30. So we'll start from the first question. So the question was, this question was written in the feedback. So I'll just tell it, because if you ask me in the class, like I said, then others will also understand it. So if you recall, you are trying to do minimize J theta. This is before we talked about regularization, right? When we did this closed form solution, vectorization, we were trying to minimize J theta everywhere. The numerical solution also we were trying to minimize J theta. So this was probably here that we wrote, है ना? When you're doing multiple linear regression, we had written H theta at point x1 is this, and then we were taking the difference, doing it in a least square sense, which I had motivated, and then we were trying to minimize this. Everybody agrees? Correct? So what we were trying to do, so this is question 1 from the feedback. Somebody asked who was shy to ask, but I'll still go over it for everyone. So you're trying to minimize 1 over 2n summation I going from 1 to n. Let's write H theta. What is H theta? H theta is theta naught plus theta 1 x11 plus still theta d x d1 or something like this, है ना? And this minus yi, this is I, sorry, and the square of it. There is no subscript here, है ना? Y was scalar. This is what we were trying to do. Correct? Everybody with me? So when we move to regularization, this slide which I am now telling you for the third time, this is linear regression, the x is still just power 1, degree 1. But assume that if x was 4 degree and it was simple linear regression in this case, or let's change this. Let's say we were doing non-linear regression. Let's say I was doing theta naught plus theta 1 tilde x and then plus we're putting I here. Plus theta 2 tilde xi square. Let's say it was non-linear but one dimensional. The x dimension is still 1. So xi is scalar is everywhere, it's just square. So there in that case you were trying to minimize this with respect to theta. Everybody agrees? And now let's say if it was 4 and you got this green curve with higher theta values, then it was highly overfitted. The variance was really large. But when you got the thetas to like 1/5 of this theta, it became, variance was less, it was not overfitting. All the power was still 4 here. For example, if this was 4, let's say, and so on and so forth, if I am just writing the exact same function here. Correct? Everybody with me? So what we are trying to say is that if you reduce the theta tildes, I am referring to them as tildes because this is in a non-linear case. When it's a linear one, then I am referring to them as theta. Okay, just to differentiate the two. So when we are trying to minimize this, so which means that reducing the value of theta actually gets you a better fitted curve. The overfitting goes down. Yes or no? So what we could do, we could just say minimize j theta plus and add all the thetas which you want to reduce. So we want to reduce theta 1 tilde till all the way, this is theta 4 tilde. So this is the reason that when you minimize the whole thing, this will also minimize along with this error function and they will go down, which you want so that it gets better fitted. That's the reason we add these and do a minimization. Because I want these values to come down and get a better fit. But then I said the minimum of this guy is tending to minus infinity and it's not a convex function. So let's do like we did this in a least square sense. So we'll add, rather than linear, we'll add them square so that the minima is 0 and doesn't go to minus infinity. It stays as a convex problem. So that is why the regularization, we call it as an L2 regularization. I didn't give you the name. You can do L1 also, which is power 1, but this is the standard one which you do. Is this clear to everyone why we are trying to do? So that we can bring the thetas down along with minimizing the j theta. Everybody okay? Should I move forward? You want to ask who was doubtful about it? Is it clear to you? Okay. If still not clear, ask me after class. I'll try to think of another way of doing it. And then came the story of lambda over 2n. 2n was normalization. Lambda was deciding how much of this factor you want to dominate. If it dominates too much, all the thetas will go to 0 and theta naught will dominate and it'll start underfitting. If lambda is too small, then this term will dominate and you'll go back to the overfitted case. I've repeated it now the third time. You have to tell me whether you get it or not, otherwise we'll stop here. Okay. So this was the first question. Second question which somebody asked and I said, why didn't you ask? I thought I uploaded this. So there was a typo yesterday and he pointed to me later on. When we were trying to do this closed form solution with the regression term here, we got this matrix which we are trying to inverse. So the dimension of this matrix is just x. So this is, I don't know if anybody else noticed or not. So this was x transpose x plus lambda times this whole big matrix 0, 1, 2, 1. And then this is inverse. So we got that since x dimension was n into d plus 1, x transpose x had become d plus 1 cross d plus 1. And here it was with respect to theta, not to theta d. So this matrix was also of the dimension d plus 1 into d plus 1. So now you're adding two matrices of same dimension. I somehow in a hurry said that we're putting them in the column, so it was becoming d plus 1 times 2d plus 2, which is not correct. You're just adding, so it'll still remain a square matrix. The reason pseudo inverse is there, we have no idea whether this will be invertible or not. If it is not invertible, then we go back to approximate inverse, which is called the pseudo inverse. Is that okay? So if you run into such things, stop me, hai na? Stop me there itself in future. The third problem, okay, we're trying to finish it. The third question, he had asked me that can we do the gradient descent, not do it individually, but do it in a vector form. So I think you worked it out. You can still, so like for the closed form solution, we are working with a matrix and vector here, but for the gradient descent, we are separately writing thetas and theta j. So you can actually combine it and do it. So you can work it out. So this was the third question. The fourth question which somebody asked, and I think many of you will have this doubt, so I thought we still couple of minutes there, so I'll talk about it. When we work from your coordinate geometry in 2 dimensions, which you study for your 12th or for your engineering, when we write y is equal to mx plus c. So this is, m is the slope of that which everybody knows, and c is the intercept where the line cuts the y-axis. Correct? Everybody with me? When we are trying to write this in a hyperplane context, I'll share this resource also on this. What did we write? We wrote it as W transpose X plus B. Correct? You can take this and transform it into this form and take this and transform into this form. That you can always do. There is no problem. So for example, let's say we were working in 3 dimension, W1 X1 plus W2 X2 plus W3 X3 plus B is equal to 0. Or if it was 2 dimension, let's say, let's not go to 3 dimension, plus B is equal to 0. You can assume that X2 is Y and try to write it as Y is equal to MX plus C. Everybody okay? So the question what he was asking is, what does this B signify here in this one? So the B in the general form of the hyperplane equation is the distance which you are away from the origin going along the normal to the hyperplane. What it means is that now there are no axes, right? In 2 dimensions, you have axes. In n dimensions, how many axes will you draw? You can't even visualize beyond 3 axes. So what you do, let's say if this was my hyperplane, well, I'm just doing n dimension and this is my origin somewhere, or maybe not draw 3-dimensional cases. Without the axis, let me draw it. So if this is my hyperplane and origin is some point 0, 0, 0, 0, which is the number of dimensions you have, this vector W, which is W1, W2 would be the normal to this. This is what we told, this is how it's defined. And when you go, like you go in the direction of this normal vector, so this is my origin. So what is this? This is defined by B. So the B value, absolute value, because it could be negative as well, divided by the norm of the normal gives you the offset you are away from the origin. So this is what it means in a hyperplane sense. Is that okay? You can convert between the two. For the sake of this class, we'll not use y is equal to mx plus c. We'll use the general form because we'll work in n dimensions. Everybody okay? All right. Last thing I wanted to talk, I know we are almost up, but I'll take 2 more minutes. I'll formally summarize this. So the feedback which you gave, which was very useful. So what is good is, of course, mostly the pace is good. The material you are finding it upload on Drive to be very useful. And you're finding the class to be engaging. So those are the top 3 things which everybody has liked in general. Even because now I'm teaching to non-CS people with seeing me for the first time. What to improve is there are many things, but what I'm already doing this, so I thought I'll emphasize it for you. They were out of whatever 60, 70 people were there yesterday, there were two people who said this is too slow for me. And one said it's a little fast for me, one or two. So I think for this fast person, you have to come to me and after class and tell me what you're missing so that I know, because I can't slow it down more than this. For those who are slow, I'll start bringing problems and you can practice on the side. So make you more challenging. So this slow fast is always a challenge to handle, especially when there are people from other thing. But what 3-4 people said is that although again this is math, okay, not okay, there are mostly people who said I'm getting the math, but there are 3-4 people who said the math is going too fast for me. So again, if this is going too much for you, then you tell me after class. And I'm meeting you almost 4 days a week. So after me, you stop me and tell me, because unless I know because according to me, I've gone to the very basics. I am feeling that I've gone more level downs than I would naturally teach, so that everybody is on board with the math. But now you have to come and tell me where you're missing so that I know and I don't repeat this. So tell me after class. So that is one thing. The two general comment which most people, so this was slow fast, which is again, I'll take care of slow fast. Math I can't take care of because like I said, you have to tell me where you're missing. But there were two things which you guys wanted. One was practice, and the second was real life problem. So this was a comment which was coming off again and again. So in terms of practice, there's a set of practice problems already for regression. Have you gone through those or not on the drive? Yes or no? So go through those. If you finish it, we'll upload more. There's the next set ready for SVM as well. Like I said, in the labs, we are doing, because we just had 2 lab or / tutorial. So you only did a numerical. Tomorrow you will do regression problems, and there's a lot more regression problems uploaded as a homework. So this is already done. You go and check. Then the SVM we'll do. SVM we'll finish, you'll do a example numerical, you do a tutorial, then uploaded problems will be there. But beyond that, if you need, then tell me. But first see how it goes. In terms of real life problems, tomorrow we'll start going through papers. And we'll start doing papers where I would want you to pick it from your domain. Machine learning is everywhere. Pick a domain and machine learning, because it's easy to publish once in sense. So there's a lot of people trying to do work in machine learning. So we'll go through the papers and we'll pick real life problems and we'll see where it is playing a role. So this will start coming from the lab. This is in tutorial and uploaded. So I think in general that was this. I just glanced through this. There were a few other comments that let's please do a project. The problem with the project is I love to do minor projects, but then Chandresh is taking after the break, so I can't interfere with and you can't finish a project before the mid-sem, so there's too much work. There were a few comments that teach for the whole semester. Of course, I can't teach whole semester because the department decided that I've got other commitments for the second half. Usually, abhi tak to I had taught the whole course. But this time they asked me to share, so that's why I'm sharing. But doesn't mean that I'll vanish, I'll be there. So if there's a background missing, like probability background, I'll come and teach even during the Chandresh's time. So you don't have to worry. So I'll be there, I am the course coordinator. So if there's any problem, you can come and tell me. So don't suffer. If you feel that you're missing something, you can always, anonymously tell me, so that we can improve. But we'll worry about it in March. Why to worry now? So somebody was writing a feedback. So that's the feedback, but thank you for writing. Okay, we'll stop. Thank you.